This is my second example. We have a beam AB which has two portions, a horizontal portion and an inclined portion. The beam is supported by two supports, a roller support at point A and a pin support at point B. The beam is subjected to a uniformly distributed load of 3 kN meter from this point to this point. We need to find the reactions at the supports. We need to find the support reactions at A and B, and as we have seen in the first example, the analysis of the beam would allow us to find the support reactions, and therefore the body to be analyzed is beam AB. So I have drawn the free body diagram of the beam right on the picture. So these are the key aspects of developing this free body diagram. First, we note that we have a roller here, right? And therefore the reaction at that point is going to be a force perpendicular to the plane on which the roller is resting. So this is the plane, and therefore the direction of the force is going to be perpendicular to that. All right, now let's call that as FA. Remember, there's no moments at rollers, right? So this support basically brings in one unknown, FA. We have a pin at point B, and therefore there will be two forces. So I mark them as Bx in the horizontal direction and By in the vertical direction. Now I want to mark the direction of FA. We note that this angle is 30 degrees, and therefore this will be 60, this will be 30, and therefore this will be 60 degrees. In other words, FA makes an angle of 60 degrees to horizontal. Like I have done in the early example, I want to take this force and resolve that into two components, horizontal and vertical. So my horizontal component will be FA cosine 60, and my vertical component will be FA sine 60. So with respect to this direction, these are the directions for the horizontal and the vertical components. Finally, I want to represent this uniformly distributed load into an equivalent point load. So the magnitude of the point load, if you recall, equals the area under the distributed load diagram, right? So that will be 3 multiplied by 4, so you get 12 kilonewton out of that, and that force is acting in the middle of it because this is a uniformly distributed load, and the centroid of that is right in the middle, and therefore this distance will be 2 meters. Before we proceed, I want to point out two new things in this problem. Number one, we have this roller sitting on an inclined plane, and therefore the force is perpendicular to the plane, and therefore the direction of the force is no longer vertical or horizontal, it's inclined. Number two, we have a distributed load, so we learn how to deal with that. Now we want to develop a plan of attack. We see that the force equation in the horizontal direction will bring in FA cosine 60 and Bx, so we're going to end up having two unknowns. Force equation in the vertical direction will bring in FA sine 60 and By, so we're going to end up having two unknowns. But if I take a moment about point B, Bx will not show up, By will not show up, and therefore there will be just one unknown in that equation. We do have three unknowns, FA, Bx, and By, so we're going to end up writing down three equations. So that's a matter of sequencing them so that the process becomes a little easier for us. So we see that the moment equation about point B is the best choice to start with. So here's my moment equation about point B. The forces to be considered are Bx, By, 12 kilonewton, Fa sine 60 and Fa cosine 60. So there are 5 of them, right? Out of the 5, we already said that Bx and By will not make a contribution to the moment equation. So we have 3 of them left in there. So this moment equation is supposed to have 3 terms. Here's the term associated with Fa cosine 60. So the force is Fa cosine 60. And the perpendicular distance, the line of action, is this distance right there, right? And that will be 3 sine 30. 3 sine 30, that's what I have here. So how did I figure that out? Well, here's the line of action, right? And the perpendicular distance will be this, which is exactly equal to this, which is 3 sine 30. And you can see this force is going to spin this point in the clockwise direction, and therefore I have a negative sign in front of that. The term associated with FA sine 60 is over here. So the force is FA sine 60, and the distance, perpendicular distance, the line of action, is from here all the way to here. So that will be 4 plus 3 cosine 30. So once again, here's your line of action, right? And this is the perpendicular distance, and that perpendicular distance will be 4 plus this distance, which is 3 cosine 30. And this too will produce a clockwise moment, and therefore I have a negative sign in front of that. So for the purpose of writing down the moment term associated with this distributed load, we use the equivalent point load. So the point load is 12 kilonewton, and that's acting at this point, which has a arm length of 2 meters from point B. So this is the line of action. This is the perpendicular distance, which is 2 meters, right? So that's what I have over here, 12 multiplied by 2. And this is going to give us a counterclockwise moment, and therefore I have a positive sign in front of that. You can see there is just one unknown FA in this equation, so this can be solved. So here are my calculations, and I get a value of 3.72 kilonewton for FA. So when you have equation like this, where each term is slightly complicated, right? So it's a good idea to simplify each term as you go along. That's what I have done here. So I simplified this, and I got 0.75 FA out of that, and I simplified this, and I got 5.71 FA out of that. And you go ahead and simplify that also. And then on the third step, you find a value for FA. Next, I write down a force equation in the horizontal direction. Since we have resolved this inclined force into a horizontal and a vertical component, forces are either horizontal or vertical, right? So only the horizontal forces will come in this equation. These are B sub x at point B, and then FA cosine 60 at this point. So those are the only two forces that are going in the horizontal direction. So they come in here, and they both go in the positive x direction, and therefore they both have a positive sign in front of them. Set it to 0, and I get a value of minus 1.86 kilonewton out of that. So here's my force equation in the y direction. We have By, FA sine 60, both of which are going in the vertically upward direction, so they have a positive sign in front of them. And this 12 kilonewton is acting vertically down, so I have a negative sign in front of that. So those are the three terms that are going to show up in this equation. And you simplify that, and I get a value of 8.78 kilonewton. Just as in the earlier example, we get positive and negative numbers for the reactions. FA is positive 3.72 kilonewton, therefore our original direction is correct, so I have marked that over here. And BX is minus 1.86 kilonewton, therefore our original direction is incorrect, so the direction has to be reversed. And BY is positive 8.78 kilonewton, and therefore our original direction is correct. Let's look at a couple of what-if situations and see how you deal with them. Number one, what if the plane on which the roller is sitting on is not parallel to this member, but rather it is horizontal? Well, you just have to remember the fundamental. The force acting on a roller support is perpendicular to the plane on which the roller is sitting, right? So if the plane is horizontal, the force has to be vertical, like shown here. Everything else will remain the same. So here they are. All these other things will remain the same as what we did earlier. So since the force is vertical, you don't even have the task of resolving the force into horizontal and vertical components. It's already vertical, right? But keep in mind, sometimes this plane could be arbitrarily oriented, like this. You just have to put the force perpendicular to the plane. That's it. What if the distributed load acts not over here but over here, like shown in this picture? Again, remember the fundamentals. Number one, the direction of this point load is going to be the same as the direction of the distributed load, and therefore the point load, resultant point load, acts in that direction. Number one. Number two, the magnitude is still the area under the distributed load diagram. which will be 3 multiplied by this distance, which is 3 meters. So 3 times 3 is 9 kilonewton. Number 3, the point load is going to be acting in the centroid of this distributed load, which is in the middle, and therefore this distance is going to be half of 3 meters. In other words, this distance is 1.5 meters. So this time, since we have to resolve this into vertical and horizontal components, you may want to put this force right at this point, because that's exactly where this force is acting, right? And this angle is 60 degrees, because this is 30, and therefore this is 60. And then you resolve this into horizontal and vertical components. So the horizontal component is going to be 9 cosine 60, and the vertical component is going to be 9 sine 60. And of course, you go ahead and resolve this FA into horizontal and vertical components. And then here are the rest of the detail. So you simply have a bunch of horizontal forces and a bunch of vertical forces, right? So now you know how to deal with them.